Science often moves forward with bold claims followed by a mountain of careful evidence. Today, we stand before one such claim, and it is a monumental one. Astronomers using the James Webb Space Telescope believe they may have found something thought to exist only in theory: dark stars. These are not black holes, nor are they simply stars that have burned out. They are a different kind of object, powered not by nuclear fusion, but by the annihilation of dark matter. The evidence points to 4 specific objects found in the most ancient corners of the universe we have ever observed: JDSG Z14-0, JDSG Z14-1, JDSG Z14-0, and JDSG Z11-0. Each one appears impossibly bright yet surprisingly compact, a point of light when the universe was barely 300 million years old. The big claim: not the first galaxies, but individual supermassive dark stars, potentially 1 million times our sun's mass. The data is tantalizing but preliminary. This is the essence of discovery. You point a powerful new telescope and see things that don't fit the models. JWST was built to peer back to the cosmic dawn and find the very first lights. Finding possible supermassive dark stars sends ripples through cosmology and particle physics. The journey has only just begun. So what exactly is a dark star? The name is a misnomer. They are anything but dark. They could be incredibly bright, shining with the light of 1 billion suns. The dark refers to their fuel, dark matter. A dark star is powered by dark matter annihilation, fundamentally different from what powers our sun. Our sun shines from thermonuclear fusion. Immense pressure and heat force hydrogen to fuse into helium, releasing energy. Dark stars form in the very early, denser universe, within massive dark matter halos, where primordial gas collapses. If the halo's dark matter were WIMPs, weakly interacting massive particles, the collapsing gas drags them into the core, raising density. WIMPs are their own antiparticles. When two meet, they annihilate, releasing heat, photons, and other particles. That heating can halt collapse before fusion starts, inflating a huge, puffy, incredibly luminous object, a dark star. Models suggest growth to enormous sizes, possibly millions of times the sun's mass. The idea, developed since June 2008 by theorists including Catherine Fries and Cosmin Ely, was fascinating but untestable until JWST. Now we can look for objects that are too big, too bright, and too compact. Exactly what these 4 candidates seem to be. Powered by dark matter annihilation, not fusion. That's the signature of a dark star. Finding a potential dark star requires specific clues. You can't just see one and say, that's it. You build a case, piece by piece, from faint light that has traveled over 13 billion years. First clue, morphology from NIRCam. JADES GS, Z14-0, and the others appear as unresolved point sources, star-like, not fuzzy blobs. Standard models predict nascent galaxies, extended patches of light. These look like single points or astonishingly compact systems. Small, compact nebulae appear around them, consistent with a massive source ionizing nearby gas. Second clue, spectroscopy with NIR spec on the brightest candidate, JADES GS Z14-0. They found a subtle, crucial feature, an absorption line at 1,640 angstroms. This corresponds to He2, singly ionized helium. Making this absorption requires strong ultraviolet radiation and a photosphere cool enough to imprint absorption. A supermassive dark star's immense gravity can maintain a cooler surface layer that absorbs interior light, producing exactly this line. It's a predicted hallmark of dark stars and one of the strongest arguments for the hypothesis. But remember, preliminary does not mean proven. The helium absorption is compelling, but the detection is weak, with a signal-to-noise of about 2. Like a faint whisper in a noisy room, an SNR of 2 is suggestive, not conclusive. At the edge of the observable universe, low SNR is common. Future deeper observations must raise it. Then came ALMA. Oxygen emission was detected near JWST, a surprise, since first-generation gas should be pristine hydrogen and helium. Oxygen implies at least one prior generation of normal stars lived and died to enrich the gas, complicating the pristine dark star picture. This doesn't rule out dark stars. It suggests more complex scenarios, co-formation in a cluster, or a merger of halos bringing metals. The oxygen is a puzzle we must solve. Next step, longer integrations to confirm or refute the He2 absorption and map the metal-rich environment. For now, the line is a hint, not proof. By the numbers, cosmic giants in the universe's infancy. The four candidates, JADES, Z14-0, Z14-1, Z13-0, and Z11-0. They are defined by extreme redshifts, light stretched by cosmic expansion. Z11-14 places them about 290 million years after the Big Bang, roughly 2% of the universe's current age. Based on brightness and models, masses could be 5 to 10⁻⁶ solar masses. Standard star formation struggles to reach even a few hundred solar masses before feedback halts growth. A million solar mass light output usually means a whole galaxy, yet these appear point-like. Dark stars, powered by annihilation, are puffier and cooler at the surface, letting them keep accreting to supermassive scales. This could solve a long-standing puzzle, the rapid rise of billion solar mass black holes in the early universe. When a million solar mass dark star exhausts its dark matter fuel, it could collapse into a similar mass black hole, a ready-made seed for quasars. That head start bridges the gap between early times and the quasars we see within the universe's first billion years. The dark star hypothesis is exciting, but the evidence is not yet conclusive. Most significant, oxygen detected by ALMA near JADES Z14-0, implying prior star formation and metal enrichment. This challenges a pristine, first-generation origin and forces more complex formation scenarios. Possibilities include co-formation with a cluster of normal stars, or a merger between a pristine halo hosting a dark star and a small enriched galaxy. Another uncertainty, the He2 absorption has SNR2. Science typically demands SNR to 5 for robust claims. At low SNR, patterns can be illusions, like seeing a dragon in the clouds. JWST offers an unprecedented view, but we're still peering through a keyhole into the cosmic dawn. Oxygen and low SNR don't kill the idea. They make the story richer and demand more data before firm conclusions. We're mid-investigation. Patience and rigor will decide what these points of light truly are. More photons, better spectra, that's how we move forward. Extraordinary claims demand ordinary alternatives be tested first. Could these be something other than dark stars? Absolutely. The leading alternative, extremely young, compact galaxies with dense star clusters. Packed with thousands of hot, massive stars, they could appear point-like to JWST, but clusters tend to produce He2 1640 in emission, not absorption. Hard to reconcile with JADES Z14-0. Another idea, an early active galactic nucleus. Yet the spectra lack the broad emission lines typical of feeding supermassive black holes. We must also test gravitational lensing effects and subtle intergalactic medium features that could mimic or alter signals. Confirmation requires ruling out compact galaxies and AGN and proving the signals are real. Only then can dark stars move from hypothesis to discovery. Skepticism isn't doubt, it's the path to truth. This discovery is a starting gun, not a finish line. Top priority, obtain deeper, higher resolution spectra of all four candidates with NIR spec. Longer exposures collect more photons and raise the signal to noise. If He2 absorption strengthens, the dark star case grows. If it fades, the case weakens. Models predict strong He2 absorption, but an absence of certain high ionization emission lines seen in clusters or AGN. Variability tests. Compact galaxies and single dark stars should be relatively stable. AGN can flicker. Long-term monitoring will tell. Higher resolution ALMA maps can localize oxygen, central concentration, or merger-driven distribution. A multi-pronged campaign, deeper data, multiple instruments, direct tests of predictions, is how hints become facts. It will take time and patience, but that is the only way to be sure. Why care about faint, distant smudges of light? If confirmed, they would revolutionize our understanding of dark matter and the origin of supermassive black holes. Dark matter is the ghost in the machine. We see its gravity. We've never caught it directly. WIMPs remain elusive in terrestrial experiments. Dark stars would be powerful, indirect evidence of WIMP annihilation. A dark star's brightness, mass, and temperature tie directly to particle mass and annihilation cross-section. We'd use the universe itself as a particle detector. And we'd solve the black hole seed problem with million solar mass collapses, providing a head start. This connects the largest structures with the smallest particles, from the Big Bang to galaxies today. We live in a remarkable era. Technology is catching up to theory. Whether these four are dark stars or not, the quest to understand them will teach us something profound about our origins. Thanks for watching. For daily deep dives into JWST and the cosmos, like and subscribe.